every Wednesday from today till December 2nd at the same time, with amazing speakers from different parts of the world and covering a variety of very interesting topics. This week, we have Ylva Gottberg, who is currently a postdoctoral fellow at the Carnegie Observatories in California, United States. She obtained her PhD in 2019 from the University of Amsterdam, and before that, she completed her master's in Lund, Sweden. She will be talking about stars stripped in binaries from cosmic reionization to gravitational waves. Ylva, thank you for accepting our invitation.
Thank you, Anna. And I wanted to start with say that I'm very happy for the invitation and to be able to join you in Brazil from the other part of the world. So there is actually like something positive with these virtual things happening, that I will be able to virtually go to Brazil. Anyway, I hope to talk about something exciting with you today, which is interacting binaries. And you can see that in the background of my first slide here, artist impression of how one star is transferring material to another star in the binary. So that's something we're going to look closer at later in the presentation. But let's start with the basics. This is a standard picture of stellar evolution as described by NASA. So what you can see here is a very simplified picture, how a protostar evolves to burn hydrogen in the center as a star and eventually swell up and then become a compact object like a white dwarf, a neutron star, or a black hole. So this picture, I say, is simplified and even incorrect in some parts, because this is describing the evolution of a single star. And especially in the high mass end, stars do not spend their lives alone. They live together with a close companion star, which completely changes their evolution and their life and how they spend their life. So how common is really these binaries? This diagram comes from Maxwell Moe and Rosanne Di Stefano in 2017, where they synthesized a survey, the results from surveys of different mass stars. So here you can see on the x-axis the mass of the most massive star in the system, and on the y-axis the fraction of such stars that are in binaries. This is a function of mass. So at the low mass end, solar type star, maybe 15% of them interact in binary stars, whilst the most massive stars, the O-type stars and so, almost all of them or all of them are in such close binaries that interaction will occur. So you can see here that there is some error bar that goes above, 1 here. And what does that mean? It means that they are prone to have even more companions than just one. Maybe they are in triple system, quadruple system. I think that the biggest system I heard about was like an octuple system. So it's really getting crazy when you get to these high masses. But today we'll stick to the binaries and talk a little bit about what can happen when stars are in binaries. So what actually happens? What does it mean, interaction? This, I think, is a really cool system to start with to show that. This is Beta Lyrae. Beta Lyrae is a nearby binary system, and so this is actually real data. What you can see here is images from the Chara array, which actually is located close to my job in north of LA. And what Xiao et al. Here in 2008 did, they imaged this system, and what you can see is that one of the stars, the donor star, the dark star in this system, which means the most luminous star, is deformed. And it's deformed because it is transferring material to the other star in the system. So the accreting star is accreting material from the first star. The donor star, even though it's the most luminous, is just 3 solar masses, while the accretor, the least luminous star, has about 13 solar masses. So it really shows that some significant amount of mass has been transferred from the donor star already to the accreting star. So this is not, interaction doesn't mean, you know, a little few, half a solar mass, a little less, a fraction of a solar mass. It's many solar masses. It's a significant change. The result is that you can see the interior of the star that is completely exposed. Another nice example, I think, is this one. It's called VFTS 352. It's a star in the Large Magellanic Cloud. And what you can see here is the light curve as the star it's a binary star, okay, reveal. It's a binary star, it's moving, and you can see a light curve as the star changes luminosity. And here is a radial velocity curve showing you how the star is moving back and forth in the binary. What this light curve is showing you, I think it's really nice, it's because it's so smooth. It is actually an over contact binary. And that, because it's so massive, it's 230 solar mass stars sharing about 30% of their mass, it really triggered quite a lot of attention. And in the press release, this binary was depicted in this way, and I think it's a really beautiful illustration. And you can see that it's sort of a peanut. It's no longer spherical at all. So binaries can really do quite exciting stuff with when they interact. And there has been several ideas about what happens in such a binary, triggering mixing, causing new fuel to be dredged into the core, etc. So that's, I think it's quite exciting. So how common are these interacting binaries? This pie chart comes from actual data. It's from galactic O-stars in clusters. In 2012, Sana and collaborators, they synthesized these clusters. They look at the O-stars and they measure how many of them have a binary companion and how tight is that. And then you can infer how common different types of binary interaction is. So I think the first thing I want you to notice with this pie chart is that binary interaction and binary stellar evolution is more common than single stellar evolution. Single stellar evolution is just this 30% here, while here we had 70%, right? About a third of the stars, they lose their envelope through mass transfer, as in beta Lyrae case. About 14 accrete material, and maybe a quarter merge during binary interaction. This interaction completely changes the stellar evolution. Here is just a few examples. I'm not going to go into detail there, but for example, what can happen is that you completely change the type of supernova, the explosion of the star. It becomes a stripped envelope supernova. The star maybe emits X-rays, which it wouldn't have done otherwise, or it triggers magnetic fields. So this is just a few results of binary interaction. But today I want to focus on the envelope stripping, which has been the core of my research during the past few years. So I have structured my talk in three little clumps. To begin with, what is the result of envelope stripping? What are these stripped stars, and why haven't we heard about them maybe so much before? They turn out to be really hot, so they emit a lot of ionizing photons, and I think that they have quite interesting implications for stellar populations, so I would like to talk a little bit about that. And more recently, I figure out that when they orbit compact objects, they can be sources of gravitational waves, and that doesn't just limit gravitational waves to compact objects anymore, but living stars are also allowed to join the party. Okay, so to begin, what are these stripped stars? So let's just make sure that we're on the same picture. Here's a little movie. So what happened here? The most massive star in the system over here, it swelled up and it transferred its material then to the second star, which spun up, reached really rapid rotation. And eventually all of that envelope is lost, and you can see the hot and compact helium core of the donor star. And this is what I refer to as a stripped star. How do we look at this more scientific way, maybe modeling way? I use MESA, which is a stellar evolution code. And here is one of the most common diagrams that I'm looking at. It's a Hertzsprung-Russell diagram where you can see the temperature going now in the reverse direction on the x-axis and the luminosity on the y-axis. This is the stellar evolution track of a single 12 solar mass star. As you can see, it evolves from relatively high temperatures to really cool temperatures and explodes as a red supergiant in a type 2 supernova. In blue shading, I show the fraction of the emitted radiation that is ionizing. And you can see that this 12 solar mass single star is relatively useless in emitting ionizing radiation. But in contrast, if the star is stripped, here's the envelope stripping phase, it instead shows that hot and compact helium core, and the star is now emitting a significant amount of its radiation as ionizing radiation. Further on, when it evolves further, it's now lost its hydrogen envelope and will explode as a type 1b supernova, so a stripped envelope supernova, which is two significant differences here. Now, I'm not the first one to make these models, and this is actually, oh yeah, that's the stripped star. This has actually been done for more than half a century, so I think this is a pretty interesting thing to show, because you probably recognize then the diagram here. This is of a 9 solar mass star. The difference is it was computed in 1967 by these people here. So these photos are from 10 years earlier, but the evolution in the computers is not that different. So here is the computer, and the lady here, she is reading the outcome of the stellar evolution code on this paper up here. So here you can see a little bit more about the computer. So it's really different, but it's an old field of research from a theoretical point of view. On the other hand, few observational counterparts have been found, and that's something that I'm going to get into a little bit later. But let's get back to my picture here. I was curious about, okay, so how do these stars look like really? What is it we're missing, why we haven't found them? So I decided to make a spectral model for this stripped star and to look into what is it they look like? Why? How are they really? So, because with this kind of stellar evolution code, the only thing that you can create for spectrum is the Planck curve, right? So here we have the wavelength, and here is the flux, and that's not very telling either about how the star looks like or how much ionizing radiation it emits. But with the spectral model, you really get a lot of details. For example, these stars emit about 83% of its flux as ionizing radiation. So to summarize, the stripped stars, what are they? They are hot, maybe 30 to 100,000 Kelvin, small, less than 1 solar radius, and they cover a range of luminosity depending on their mass, so they may be 10 to a million solar luminosities. And since they are the exposed cores, they are helium-rich and hydrogen-poor. So then I would usually ask, so what kind of star do you think that is? And maybe there is a group of people who would say, hey, I know what kind of star that is. That's a Wolf-Rayet star. But maybe some other people would say, no, but I know this is a subdwarf. Okay, so none of these are wrong. If we look at the mass range of so helium stars, that we can call them also, on the low mass end, there are the subdwarfs, but on the high mass end, there are the Wolf-Rayet stars. In between, binary interaction predicts that there should be stars, and hopefully in the future, I can talk a little bit more about that, but I will refrain to future slide now. Okay, so I wanted to, I found this by computing stellar spectral models for my strip star evolution models. And this is how they look like. So this is all in one figure. Here's again the wavelength and the flux, and the mass is increasing as we go up here, so from the purple to the blue to the green. If we look at the optical spectrum, we can actually see that that the spectral features are exactly like this. So this is not the most amazing slide I have, but luckily now with the virtual, you can actually look close to a computer here. So you can see the absorption features, which is characteristic to a subdwarf in the purple side down here, and the emission features that is characteristic to Wolf-Rayet stars at the top part. In between, there is a sort of transition spectrum where there is a mix between absorption and emission. So we have some emission features and some absorption feature. And this is now a prediction that came out from my spectral models, a sort of bridge from the subdwarfs to the Wolf-Rayet stars. So these types of stars should exist. And in fact, there was a recent survey that discovered a few first of these. It was in the Magellanic Clouds. So it was pursued by Phil Massey and Catherine Nugent, and they tiled the large and small Magellanic Cloud with narrowband filters. So let's look at the narrowband filters. So they were looking for this Wolf-Rayet feature here, which is a helium-2 feature. And they used this WN narrowband filter and compare that with what was in the continuum here in the green filter. So if something would pop up, if there would be a difference between the images on these two filters, it would mean that a star would have then an emission line, and that way you can find Wolf-Rayet stars. So what they found 10 new special type Wolf-Rayet stars, these stars with both absorption features and this emission feature. That was then what they picked up in their narrowband survey. And this I thought was really exciting because it actually completely, it matches really well. This is just an overlay of one of my models. And what to note is that the absorption features match with, they coincide with the observed features and also this emission feature here. So whether these stars that are called WN303 stars in fact are stripped stars in binaries, I think is still debated because their binary nature has not yet been determined. But what you can say from this is that it is a hot star with helium features, so that you can see it's hot, and it has a weaker wind because the emission features are not very strong, and emission features are correlated with the wind. So I think that still need to be investigated a little bit further, but I think that they are really exciting to learn more about these envelope stripped stars in general. Now, if we look at again the theory predicts that about a third of all massive stars should get stripped. But actually in observations, we have about a handful confirmed cases where we have a binary with a stripped star and a companion star. So that's not so many. If we include also some candidates, maybe there is a dozen. And that doesn't really add up to the theoretical predictions. We would need many orders of magnitude more of these stripped stars. And it made me ask, do we have a paradox here? Is the stripped stars missing? Is the theory wrong? And that would be quite devastating for example, the theory of binary neutron star creation or binary black hole creation, for example. Or is it just that we haven't found these stars? So I hope it is that we just haven't found these stars, and I believe that the reason is that they are often so extremely blue, so ionizing, that they are very, very faint in the optical, and that causes then the companion star to completely dominate and outshine the stripped star. So to show this, we actually started an observational survey now at Carnegie, together with two collaborators at Dunlap Institute in Canada with Maria Drought and Bethany Ludwig. We developed a method to identify these stripped stars. So if we look at a regular color magnitude diagram of a stellar population, this is now a stellar population model. In blue, you can see the binaries that have a stripped companion, and in black, that's basically the regular main sequence stars or binary main sequence stars or so. And here is the color. So this is blue over here, and that's red over here, and this is just brightness. So blue stars should turn out on this side, right? So we would expect striped stars to end up here. But as you can see, they typically overlap with the main sequence, making them really hard to identify. However, if you look in a UV filter, so this is the UV filter from Swift that we used, for example, you can see a larger fraction of these striped stars separating out here into the very blue part of this color magnitude diagram. So we use this technique and then follow up with spectroscopy, and we found quite a few candidates actually. So we're in the process of analyzing the data and determining stellar properties and how wrong my models were and all of this. So that's quite fun, and hopefully next time I can show you some more about that. So that, I hope, give you a little view of what are the striped stars and why we haven't seen them. Now I want to go into more implications, the ionizing photons. And I have two parts. The first one is, what is their effect on the host galaxy, and how can we use that to understand whether there is binaries in distant galaxies? And also, what is their effect on the reionization? Maybe that's more evident because of the ionizing photons. Okay, so to begin with, what are the common sources considered to emit ionizing radiation? Typically, we start with two. Okay, so there is the accreting supermassive black holes in center of the galaxies, the AGN, and then we have the stars. Okay, so now let's look at the stars. So on the massive stars, we usually think about the massive stars, and they are separated into these Lyrae stars, which are the late evolutionary stages of very massive stars, and the OB-type main sequence stars, which are really massive. These are what are traditionally included in spectral population synthesis codes, so codes that are used to measure star formation rates or ionizing emission of galaxies that you can observe the composite spectra of the entire galaxies. However, there is also rotating stars, maybe they would contribute, and they are sometimes included. But there is X-ray binaries, there are striped stars, and they can come from low mass stars too. And then there are the post-AGB stars and the creating white dwarfs. So we have a whole variety of different type of ionizing sources that we can do a lot of work on. And it's starting to get included. I would like to emphasize, especially certain type of binary products have been included in the BPAS code created by J.J. Eldridge and Elizabeth Stanway in the past few years. So that's quite exciting, but I think there is still a lot of work to do. So I could sit down and give a talk about lots of things here, but I want to focus on the striped stars, both as an example, but also because they are a very common type of binary product. So not just because they're exciting, but also because you can use them as a probe for finding binaries, interacting binaries, because they are so very different from a regular main sequence star or a giant star. Now, so if we look at a starburst type galaxy, so a co-eval stellar population, this would then be the time after the starburst on the x-axis, and here the logarithm of the emission rate of ionizing photons. In green, you can see the contribution from the massive stars, and after about 3 million years, it really drops. Imagine this slow scale, it really drops super rapidly. If you include the striped stars, so this model that I created, you can see that the contribution of ionizing emission at late times, between like 10 to hundreds of millions of years, is increasing by several orders of magnitude, making an old stellar population ionizing. And this is something I think related, has been observed already and sort of explained by low mass striped stars, which is the UV counterpart of this. It's called the UV upturn. It was found in old red galaxies without star formation that they have UV emission, which is not expected by single stars, all single stars. So Sun and Han in 2007 explained this by the creation of subdwarfs, or low mass striped stars, through binary interaction at late time. So in his model here, here's the spectrum of the stellar population at 10 million years. That's the UV. Here's the ionizing emission. with time, the UV flux decreased and the spectrum became softer, but after about 1 gigayear, there was a boost in this UV emission, and that's called the UV upturn. You can see something similar if we include the full mass range of the stripped stars. So here is after 3 million years, and you can see the ionizing and the UV part of these massive stars that are only showed in this diagram. But after about 10 million years, when the stripped stars are formed, you can see this huge boost in ionizing emission in the short wavelength over here, compared to then for the single stars in green, which have completely decreased at that time. This continues 20 million years, 50 million years, 100 million years even. There is ionizing emission from the stripped stars. And then this is just to show that my model reproduces then this UV upturn after about a gigayear. But the question is, like, here you can see that there is a lot of extra ionizing radiation, but the stripped stars in the UV and the optical range, they are really faint. So how do you actually see them? How can you check whether the model is right? Is there, because a model, in my opinion, loses a lot of its value if you cannot test it with observations. So just to give you an idea, this is work that I'm still really into. If we simulate here that these stars here being a galaxy and they emit light here, some of the light would reach this telescope that you have. Then, because the stripped stars are so faint in the optical and the UV, you would probably not see that in the telescope, because there is no telescope that can really see the ionizing part very clearly. And simply because the Earth has so much neutral hydrogen around it, so if we would have it, it would still be blocked by that hydrogen. And that means that the stripped stars are basically invisible in the UV and the optical range. But we still have hope, because actually galaxies typically have some gas. So if the light is shining on that gas, the gas is reprocessing the light. The gas gets excited and ionized, and then it shines in, for example, emission features or and of different species of elements. So if, for example, the ionizing emission of the stripped stars, it creates a certain type of element, it can maybe be traced in this way. So I want to show you a little bit more how do I think about this. This is now, again, a spectrum. Now I flipped it around. This is photon energy. And so this is high energy photons here, and this is lower energy photons, but it's normalized here at the ionization threshold of hydrogen. And this in gray, you can see the hardness or softness of the emission from a really young stellar population, including only massive stars. If you include the stripped stars, the hardness of this radiation is really increasing. So you get much more of these high energy photons, and these might then affect the nebula. For example, these are the ionization thresholds of neutral helium to ionized helium, and from ionized helium to doubly ionized helium. If then the gas gets ionized, even to completely ionized, you would be able to see lines of that helium recombining, and that could produce, for example, helium-2 emission lines. But as you see, it's relatively faint, so maybe this is promising, maybe not. But there is other lines you can look for. For example, there is carbon-4 can be ionized, and that's a really highly ionized line that doesn't very often happen for the massive stars. Or the ratio maybe of oxygen-3 to oxygen-2. So I think that this is a promising avenue to look for some smaller signature maybe, or a highly ionized nebular features, to search for these binary products and use them to infer the presence of binaries in unresolved stellar populations. And this might even be possible at very large distances if you have a sufficiently sensitive instrument. And because the galaxies are typically very small if they are in the bursty regime, and then they are also fainter. But we did an investigation together with Amy Sekunda at Princeton, where she used my model for including the stripped stars in her cosmological simulation, which now has many of these little halos containing each a little stellar population. And so here is the halo mass, and that's the emission of ionizing photons on the y-axis. And what she found was that when you account for only single stars, this is now in purple here, these purple dots, the ionizing emission is quite low. But when you include the stripped stars, in about 70% of these galaxies, the ionizing emission is boosted by more than 100 times, which makes these galaxies look completely different. So I should say that, yes, most of the ionizing radiation still comes from the most massive stars, and they have the highest rate. But the majority of galaxies would look different. And she recently checked also the brightness of these galaxies. So I should say this is a redshift of 7, and that could be detectable, for example, with James Webb Space Telescope. So we hope to develop this idea further to better understand how we can detect whether there would be stripped stars in these super small galaxies. And this raises some questions, both how do those galaxies look like, and also, are they actually going to emit all that ionizing radiation into the intergalactic medium? Because they are so small, there are holes in the gas, so this might easily emerge. And that idea triggered me to check what could be the contribution of the stripped stars to cosmic reionization. So in total, stripped stars contribute maybe about 5% of the total produced ionizing radiation of a stellar population. So massive stars are still much more efficient in creating ionizing photons. But since stripped stars are formed very late, after tens, hundreds of millions of years, their ionizing photons can actually emerge into the intergalactic medium, since then the gas of the nebula has been dispersed. So taking a simple model for how these clouds work and an analytic approach actually for the cosmic reionization, I could find that about stripped stars maybe contributed with 20% something like this, of the ionizing photons that cause cosmic reionization. So I thought that was fun, but I think it's good to think about in which way you can check this. And as I mentioned previously, so this is again the spectrum of now basically the entire all of the galaxies in the early times, and this is now showing the ionizing emission with only single stars. And if you include the stripped stars, you get a little hardening. And this hardening can, for example, be sufficient to ionize circumgalactic medium, causing, for example, highly ionized carbon. And this has been recently detected in little clumps in the intergalactic medium. Or, for example, it can heat the intergalactic medium a little bit. This is a little bit more uncertain, this part. But it's some rough ideas that I hope to also develop further later. Anyway, so with that, I would like to wrap up the part about the ionizing photons and continue to my last little piece, which is about how these envelope stripped stars can be sources of gravitational waves. And that's my most recent project, so I'm happy actually to show it to you. So let's start with reviewing a binary evolution channel, the standard binary evolution channel actually towards the merger of, for example, a binary neutron star or a binary black hole. It starts over here with 2 main sequence stars. The most massive star in the system will fill its rush lobe first. It expands first and fills its rush lobe, transferring the envelope to the companion star, which leaves then a stripped star. Eventually, that star is creating a compact object. And if this system then remains bound, it will eventually likely initiate a common envelope phase because of the differences in mass of the two components. If it manages not to merge, what is left is going to be a short period binary of a stripped star, the stripped core of now the second star here, and the compact object. In case this tightens because of gravitational wave radiation or because the stripped star swells up, it can start mass transfer. But eventually that stripped star will also create a compact object. If it remains bound, then you will have a double compact object, and that eventually merges into another compact object. If we think about now the gravitational wave frequency of binaries, it's just related here with the period in a very simple way, in the approximation. And the period of these double compact object binaries are typically can be orders of seconds, which then corresponds to gravitational wave frequencies in the LIGO band. So that explains, of course, why they built LIGO there, and that LIGO can detect this. However, binaries here with a stripped star, they can have periods as short as hours, and that is sufficiently short for having these longer frequencies that should be detectable by the proposed and now funded mission LISA, which is going to focus on the somewhat longer wavelengths of the gravitational waves. And so I thought that that was quite exciting, and I thought maybe we should make a model about this. Everybody just talks about double compact objects and how they emerge, but actually here we have some living stars that might create gravitational waves. So I used my population model actually to create a population of stripped stars orbiting compact objects. So I will walk you through this figure. Here is now the frequency of gravitational waves. And on the y-axis, we have the dimensionless strain. So that's how much, how loud the signal is. This in gray is the sensitivity curve of LISA, and sources that are located in this white region here, they can be detectable by LISA. My population model ends up here, so most of the stripped star binaries will not be detected, but there is there is about 5 sources in this particular run that I found have a signal to noise ratio above 5. And so that means that they would then be detectable by LISA. Of these, about 4 are lower mass stripped stars orbiting white dwarfs, but 1 was a stripped star orbiting a neutron star. And this matches relatively well with already observed systems. There is 2 observed systems, CD-30 and CTFJ2130 here, that are thought to be LISA sources. And this already is, I like it a little bit that it's intention, but CTFJ2130 has a shorter period than what I allow in the model. And that would mean that stripped stars may be even smaller than what I assumed, and might have even shorter periods, which would, if you imagine this population moving in this direction, would allow for even more of these sources being detectable. So actually detecting these stripped star binaries, and that's double white dwarfs, would help understand what is actually the size of a stripped star, so constraining binary evolution, and understanding what happens when the stars start interacting during this phase. And since this is a phase right after the very uncertain common envelope phase, actually understanding this population would give us a feeling for what is the outcome of common envelope, and maybe some constraints from the other direction, what does it actually lead to. So since LISA is going to be launched in about 15 years, I thought maybe we should start now. And in the closer future, I think that we can detect these systems with electromagnetic radiation, which is really an advantage in comparison to many of the other gravitational wave sources, which really don't shine that much, to be honest. And so just from the brightness, you know, they are much brighter here, between 10 and the 20 magnitudes, compared to the double white dwarfs, which are like 30, 40 in general. They should have some variability. Just because they are very tight, the strip star becomes tidally distorted, and when it orbits around, you can see different amount of the surface, and that causes something called ellipsoidal modulations. So that's actually how Thomas Kupfer, my collaborator, found the CTFJ 2130, because it had a relatively strong ellipsoidal modulation. Also, they should have really high velocity shift, radial velocity shifts, because they are so tight binaries. And so with upcoming surveys like SDSS5 or maybe WEAVE, or I have one more there. Yeah, foremost, we might be able to locate many of these to target strip stars and see whether they have shifts like that. Oh, yeah. So to summarize, I had these 3 blocks, and I will now convert them into my conclusion. So instead of what are strip stars, I hope to have shown you, we started to find and characterize these strip stars now. And this will be important also because they have an important ionizing contribution, which can hopefully help to understand binaries in distant universe, and follow maybe even interacting binaries over cosmic time. Yeah, I think that's actually really exciting. Finally, since they are so small, they can actually be detectable as gravitational wave sources when they orbit compact objects. And so there's many different avenues to follow when you work on stars, and I think that's something really exciting. So with that, I would like to thank you for your attention.
Thank you, Ylva. Virtual claps. Now it's